All right, gents. So we have been solving a bunch of antiderivative problems. So what I want to talk about today is something called particular solutions, which is, it kind of solves the question of why do we always do plus c? So if you remember the plus c in an integral, the plus a constant, is because there's an infinite family of solutions. There's an infinite family of solutions. When we start looking for particular solutions, we're gonna want one of those solutions, and it might sound like it could be kind of hard at the beginning, but the method is pretty easy. So let's talk about it. So we want to find the equation of the function whose derivative is 2x minus 7 and passes through the point 1 comma 3. So this is a specific example of a particular solution problem. The derivative is 2x minus 7. So if I know what the derivative is, I can figure out what the original function is by taking the antiderivative, or the integral. So I take the integral of 2x minus 7 dx. This is an easy one. I get 2x squared over 2 minus 7x plus c, which is x squared minus 7x plus c. All right, so here's my function. And I'll write it down here in a different color. F of x equals x squared minus 7x plus c. All right, and now we have the issue, we have this c, and we want to go through the point 1 comma 3. So how do I do that? Now, if you remember this point, 1 comma 3 is on the function f of x. If when I plug it in, if I plug it into f of x, this equation is satisfied, so I don't get any contradictions. So let's see what happens when I plug 1 in for x. I'm going to get f of 1 equal to 1 squared minus 7 times 1 plus c, which is what? Negative 6 plus c. Right? So that's f of 1. For 1 comma 3 to be on our graph, on our function, we need this to be equal to the 3. So we get c is equal to 9. And my function is f of x equals x squared minus 7x plus 9. Just a little bit of pre-calculus snuck into our calculus. Not a big deal. Not a big deal. All right. Problem 2. Now we get into like word problems, and the word problems get a little trickier because we need to interpret it correctly. We're having soup being poured into a pot at 23 degrees Celsius. So this is its initial temperature. Initial temperature is 23 degrees Celsius, and it's heated at a rate of R of t, degrees Celsius per minute. After 4 minutes, what is the temperature of the soup? So R of t is the rate the soup is heated. So I have that the temperature, I'll use a capital T for temperature, the temperature, which is a function of time, is going to be the integral of R of t, the rate that is changing, dt, right? How do I get from a rate of change back to the original function? I take the antiderivative. So I need to take the antiderivative of 30e to the minus 0.3t, which is 30 times the antiderivative of e to the minus 0.3t. And now we need to use our fancy techniques of a u substitution. U equals negative 0.3t. du dt equals negative 0.3, which gives me that du is equal to dt over negative 0.3. I want dt, sorry, dt is equal to du over negative 0.3. I lost some dt's over here as well. All right, now make our substitution. I get 30 integral e to the u du over negative 0.3, which is equal to, if I bring the negative out, so I get negative 30 times negative 0.3, that's Let's just write it. So this is negative 30 over 0.3, integral of e to the u du. This is negative 100, integral of e to the u du, which is equal to negative 100 e to the u plus c, which is equal to negative 100 e to the negative 0.3 t plus c. All right, so there's our function, and we need to figure out what c is. And this is where we have to do a little careful reading of the problem. Soup is poured into the pot at 23 degrees Celsius, and then it's heated. It's poured into the pot at 23 degrees Celsius, and then it's heated. So what do we have to do? Based on this fact, that's the initial temperature of the soup, right? So our temperature of the soup, our function for temperature, we calculate all the way down here as this guy. Our initial temperature is 23. So I'm going to have T of 0, our initial temperature, is going to be equal to negative 100 e to negative 0.3 times 0 plus c. Negative 0.3 times 0 is 0. E to the 0 is 1, so this is negative 100 plus c. And we want this is our initial temperature, so it's equal to 23 degrees. Equal to 23 degrees, so we get c is equal to 123. And there's our function, our temperature function, T of t, is negative 100 e to the negative 0.3 t plus 123. Now I want to know what the temperature is after 4 minutes, so I just plug in 4. Temperature of time 4 is negative 100, e to the negative 0.3 times 4 plus 123, which is the number negative 100 e to the negative 0.12, negative 1.2, excuse me, e to the negative 1.2 plus 123. And you can pop this into Desmos and get your numerical answer. But there's our temperature of our soup after 4 minutes. All right, next victim. Got population growth of a town. And we're starting with the year 2000. So here's the population. This is the rate of change of the population of the town. We want to know how many people. If you read the problem, we want to know how many people. So we want to know the population, not the rate of change. So we take the integral of the population, of the rate of change. We have the integral of 300 e to the 0.7 t dt, which is 300 integral e to the 0.7 t dt, which is equal to, what, 300, we need to make a u substitution, so u equals 0.7 t, just like the problem above, dt is going to equal du over 0.7. So when I make my substitution, I get 300 over 0.7 integral e to the u du, 300 over 0.7. Can I do that in my head? I don't think so. So this is just 300 over 0.7 times e to the u plus c. If I take the integral, e to the u, and plug our u back in. So this is 300 over 0.7 e to the 0.7 t plus c. All right, and now here's where we have to be careful. This is our population function, so population over time is this. We need a little equal sign. Population over time is this function. If I want to know the population in a given year, I just plug that year in a kind of special way into our function. So this is a function which starts in the year 2000. So the year 2000, really in this function, this is year 0, making 2007 year 7. That's year 7. So in year 7, we know how many people there are in town. There's that many. So I can say P of 7 is 300 over 0.7 e to the 0.7 times 7 plus c, which is 300 over 0.7 e to the 1.4 plus c. I need this to be equal to my population in this year, which is 1200. So I get that c is equal to 1200 minus 300 over 0.7 e to the 1.4. If I solve for c, just subtract this stuff over to the other side. All right, so then if I want to know my, c now, I want to know the population in the year 2012. This is going to be year 12, right? Because we started at year 0. So I do P of 12 is going to be 300 over 0.7 e to the 0.7 times 12 plus 1200 minus 300 over 0.7 e to the 1.4, because we're just trying to figure out what c is. So this is our c. It's a number. If I want to do the population in year 12, I just plug 12 into the function. All right, I'll give you a moment to think about that. Make sure you're okay with that. All right, last one. Problem 4, water is being removed from a tank at this rate. Okay, so if this is the rate that water is being removed from a tank, if I take the integral of it, I get 2 over t dt, which if we do all our tricks, we get 2 ln of t plus c. So this is how water is being removed from the tank. This is the function. I'll call this big F of t. This is the amount of water removed. Amount of water removed. Okay, it's the amount of water removed. Now we have to be tricky about figuring out what C is. Initially, I say f of 0, after no time, how much water is removed? Well, this is a bad question. Let's make this t minus 1. Make this t minus 1. We get some undefined stuff going on here, which will put a t minus 1 in here. Minus 1, and this will be a t minus 1 over here. All right, even again, using u substitution, you're going to guess what you're going to get. So f of 0, which is going to be 2 ln absolute value, 0 minus 1, plus c, which is 2 ln of 1 plus c. Right, and we'll simplify this again in a little bit. Now, what is it going to be equal to? Well, how much water is removed at time 0? We haven't removed anything yet. So the amount of water removed has to be equal to 0. And what do we do to figure out, again, what c is? We'll simplify a little further. ln of 1. Well, this is the absolute value, of negative 1. So this would be 2 ln of 1 plus c equals 0. ln of 1 is 0. So this is 2 times 0 plus c equals 0, and we get c is equal to 0. C is equal to 0. Okay? So the amount of water removed from our tank is 2 ln t minus 1 plus 0. So it's 2 ln t minus 1. This is the amount of water removed from the tank. All right, the tank starts with 1 foot in it. I want to know when the tank is empty. So that means I want to know when the amount of water that is removed equals a foot, right? Now we have to notice our rate is in inches. So this is going to have to equal not 1, but 12. It needs to be in inches. So I need to know when this is 12. So this is when ln absolute value of t minus 1 is equal to 6. Divide both sides by 2. Divide by 2, divide by 2. All right, and then what do we do now? Well, this is, if I can e both sides, if I e both sides, I actually get the right answer. So I go e. So e and ln always cancel. So it's the absolute value of t minus 1 equals e to the 6. If you remember what absolute value problems, we actually get 2 answers. We're going to get 2 answers. We're going to get t minus 1 equals e to the 6th. And we're also going to get t minus 1 equals negative e to the 6th, right? We need to figure out when we're equal to the positive and the negative. So we're at time e to the 6th minus 1, plus 1, e to the 6th plus 1. And we're at time negative e to the 6th plus 1 if we solve these. And notice that since this is a time, we actually only get this answer because we need time to be positive. Right, so we're at time e to the 6th power, e to the 6th power plus 1. All right, and that's that. Good luck. I think I have 4 problems for you. 3 I made my own and 1 you have to make on your own.